Now we've completed our discussion of the first class of carbonyls, the aldehydes and ketones. What we're going to move on to now is to talk about the second class, which incorporates the carboxylic acid derivatives. Okay, so as we learned about with aldehydes and ketones, the type of reaction that they're going to undergo is a nucleophilic attack, but it's basically going to give an intermediate like this that really all it can do, all this intermediate can do, is to protonate. And then we've learned about a lot of processes that involve the further loss of that hydroxyl. But fundamentally speaking, the carbonyl reaction really only just involves nucleophilic addition protonation. So it's overall an, an addition reaction. Okay, so it's just an addition of a nucleophile and a proton to the carbonyl. With carboxylic acid derivatives, something significantly different happens, and that has to do with the fact that we're going to have a heteroatom attached to the carbonyl as opposed to a hydrogen or an alkyl group. Okay, so we have a heteroatom, and what that means is that when a nucleophilic addition occurs, right, there's the same general way that aldehyde and ketone happens. We get to this tetrahedral intermediate, but now in this case, this can collapse out. The oxygen can sort of dump back down and spit out whatever that heteroatom is, okay? And that then gives you overall a substitution reaction, okay? So this is overall class of reactions that are known as nucleophilic acyl substitutions, or SNAc for short, okay? So that's, this bottom line is the reaction paradigm that we're going to do almost exclusively for these carboxylic acid derivatives. Now here is basically the zoo of species that we're going to talk about. They all fall under this general heading, and what's different here is the nature of that heteroatom. So we're going to talk about carboxylic acids themselves. We're going to talk about esters, which are really just substituted acids. We're going to talk about a lot about amides, very important functional group, acid chlorides, some species that are important and reactive, but probably we won't spend as much time, anhydrides, imides, and then some other things which certainly are relevant. So like thioesters are biologically relevant. We'll talk a little bit about that. And then this last category, this doesn't look like it fits the pattern, and in some ways it doesn't, because it doesn't have a carbonyl. But it turns out that nitriles are actually in the same oxidation state as carboxylic acid derivatives, so it really makes sense to talk about them in this section as well. So we'll talk through all of these characters. So let's just talk a little bit generically about the nature of nucleophilic acyl substitution. So as I just showed in the PowerPoint, what we are doing here is adding a nucleophile to the carbonyl. Okay, so the first mechanistic step is to simply just do the nucleophilic addition, and this is really identical to what we saw with aldehydes and ketones. Okay, so we get to this type of tetrahedral intermediate. Okay, and then as we said before, the collapse can then happen. Okay, so we're going to get our substitution product, and we spit off that X minus. Now, in almost every case, the rate limiting step for this process is going to be the first nucleophilic attack. That's going to be the difficult step. You're taking two molecules and asking them to combine into one, and it's just tends to be the high energy step. Okay, so what that means is that the nature of the carboxylic acid derivative, and specifically especially the nature of that X group, is really going to dictate the reactivity of the carboxylic acid derivative. Okay, so what we see is a reactivity trend that, and I won't do all of the derivatives, but it looks like this. So amides are going to be the least reactive to this type of substitution, followed by esters, and then things like anhydrides. Okay. And then most reactive of the things we'll talk about are acid chlorides. And now if you want to tie this back to something that you learned before, these trends, if you think about these substituents here, these trends actually are essentially exactly the same that you learned in the aromatic section. Okay, so we're doing a nucleophilic acyl substitution, and you can think about the reactivity trends that you learned about for nucleophilic aromatic substitution, or the reverse of the EAS reactions. Okay, so remember we learned that nitrogen is most donating, followed by oxygen, and then things like halogens are mildly deactivating. And that trend basically works the same in this case, except instead of it being attached to an aromatic, it's attached to a carbonyl. Okay, and so the probably the easiest way to think about these reactivity trends is to think about the resonance forms. So in the case of an amide, the very important resonance form that we could draw would be where the nitrogen lone pair actually donates into the carbonyl. Okay, so we would draw this resonance form for an amide, and you can see that hopefully that this actually places a lot more electron density at that carbon. Okay, because it's got both the the electrons from the carbonyl and now also this really juicy lone pair from the nitrogen that's really dumping into that carbon. And so hopefully that makes sense, that then a nucleophile is going to have a harder time adding to that carbon because it's just more electron rich. Okay, and this, by the same token, we could also then draw the resonance form of the ester, the same sort of situation. But you can see where this thing looks like an aminium ion, this thing now looks like an oxocarbenium ion, and this is less stable than an aminium ion. So it would make sense that this is more reactive than an amide, but still esters are a lot less reactive than aldehydes and ketones because an oxygen is much more donating than an alkyl group or a hydrogen, just like you learned in EAS reactions. Okay, and then you could go all the way down to the acid chloride. Of course, you remember that a chloride can be a resonance donor, right? So we could write this resonance form, and it maybe has some relevance, but remember that the dominant effect with the halogens is actually one of induction. So they are inductive withdrawers, and that actually turns out to be the dominant factor for acid chloride. So that's why they're most reactive. These are going to be very powerful reactants in these nucleophilic acyl substitution chemistries. Okay. So anyway, what we're going to see as we think about the chemistry of these derivatives, basically what we're going to do is to talk about reactions where we're interconverting between all of these derivatives. So we're going to take acids to esters and esters to amides and acid chlorides to amides and what have you. Okay, so that's sort of the whole name of the game in this section. But there's kind of now this hierarchy that we're going to have to follow based on these reactivity patterns. And what that means is that the most reactive thing, acid chlorides, this is going to be very useful for generating all of the other derivatives. So we can take an acid chloride, and by adding the right nucleophile, we can convert it into an acid anhydride. Of course, we can also do the chemistry that would take us to a ester. Right? We just add the right nucleophile to do that, which we'll talk about, and then we can add a different nucleophile and go to an amide. Okay, so all of that's going to be very, very simple. On the other hand, we can take an acid anhydride and go to the ester, or we can also go to the amide. We can take an ester and go to an amide. Okay, but what we won't be able to do directly is to take something that's lower on this reactivity chart. So here we're doing reactivity. Okay, as we go up here, we go up more reactive down to less reactive. We won't be able to take something that's of lower reactivity and directly get it up to a higher reactive thing. So you won't be able to take an ester and directly convert it to an acid chloride. You won't be able to take an amide and directly convert it to an anhydride. That's just not going to work. But anything that's higher up in this hierarchy can very easily be taken down. Okay, so we'll see we'll see that chemistry. So if we want to convert an amide to an acid chloride, it's possible, but you have to go a roundabout way. Okay, so that's the effect of the substituent, sort of the heteroatom substituent on a carboxylic acid derivative. There are other factors that can impact the reactivity profile of one of these derivatives. So one is sterics. Okay, you've learned again and again that sterics plays an important role in reactivity. And so as you might imagine, if we're doing a nucleophilic attack at a carbonyl, the more sterically hindered the carbonyl is, the less reactive it should be. And so that's exactly what we see. We could do a simple reactivity trend here to illustrate the point. So here we would have, this is called acetyl chloride, and as we start to bulk up the alpha position, we are going to make this acid chloride less and less reactive. Okay, so it's going to be a slower and slower reactivity as we add nucleophiles to these things. Okay, and then least reactive here would be all the way to here where we've got this fully substituted carbon. Okay, so most reactive down to least reactive, as you're just simply hindering the nucleophilic attack to the carbonyl. Okay, that's very straightforward, I think. Now the other thing that can impact reactivity is the electronics. So we just talked about the electronics of the leaving group itself, this heteroatom, but the electronics of the thing that's on the other side of the carbonyl also will have an impact. Okay, so we're primarily talking about the alpha substituents in this case. It's not the only factor, but those are the most prominent. And so what we're dealing with here is the idea that we've got some substituent, let's just call it S, whatever, or maybe, yeah, we'll just call it substituent. And so this group is going to have some capacity of electron withdrawing or donation via induction, okay, primarily. And so we could draw, you know, a dipole moment, for example, and that's going to impact the potential reactivity of the carbonyl. And of course, the more electron withdrawing that substituent is, the more electron deficient it makes the carbon, therefore the more electrophilic it becomes. Okay, so that's basically the deal. And we could demonstrate this by, again, just showing a quick series of acid chlorides. So there's acetyl chloride again, and in this scenario, that's going to be the least reactive. And if I were to, say, put an electron withdrawing fluorine attached to that position, obviously that's a strong electron inductive withdrawer, and that's going to make this acid chloride more reactive than that one. And then if I were to put even more of those groups, well, okay, now this is going to be very reactive because there's all of this dipole moment here from those fluorines is pulling the electron density away from that carbonyl, just making it all the more electron deficient. So that's going to increase the reactivity of the carbonyl. Okay. All right, so we're going to see a bunch of different reactions. We'll talk about the different derivatives as we go through this, but they're all pretty much the same. They follow the same general mechanism, and there's just a few differences. But we're basically going to talk about you know, a variety of transformations of these acyl derivatives, or these carboxylic acid derivatives, and they kind of all fall under the, you know, a few general headings. So on the one hand, we could reduce these things, and we already talked about hydride reductions when we talked about the synthesis of alcohols and carbonyls. So we could either do a reduction, and of course you remember that this can go further as well, right? We talked about the addition of organometallics such as Grignards, okay, and that's going to go to form ketones, and of course you remember that this can also go further. So depending on exactly what we're doing there, we might get the carbonyl or the alcohol. Okay, so this is reduction. This is alkylation. We can hydrolyze. So if we've got an ester, for example, we can hydrolyze. So we're going to use formally water as the nucleophile, and this will get us back to a carboxylic acid derivative, and this is a process called hydrolysis. Okay. We can convert a derivative to an ester by using an alcohol as a nucleophile. So that example, treating an acid chloride with an alcohol will get us to an ester. That is called alcoholysis. And then very important reaction, if we use an amine, we will get to an amide, and this could be called aminolysis. It's usually just called amide formation, but technically it's an aminolysis. So those are basically the transformations we're going to discuss, by and large, the few variations, and we'll just see how these things differ based on the functionality that you're using.